Today I'll talk about our paper UTFix change-aware unit test repairing using LLM. I'm Shanto Rahman. This work has been done when I was interning last summer in AWS. So in the evolutionary software system, we very frequently update the software. So we need to update the software to repair the bugs, to add the features, and many more reasons. And when developers make their changes in the code base, many often they forget to update the test case. So as a result, spurious assertion failure or reduced code coverage can happen. In one study, Meta showed that there 14 to 22% of the software failures are coming from outdated tests. This highlights the need to keep tests in sync with code changes to ensure software reliability. Here is an example of a unit test that is taken from an open source Python project. Here there is a focal method. The main responsibility of this test to check if this focal method is working correctly or not. So focal method can be any method that exists in the code base. So let's assume the scenario that this focal method is now updated by the developers, and here that red part is representing the deleted code and the green part is representing the added code. So here the main changes is happening based on the value of force. From the test code, we see the value of force is set to true. When it is true, then the else branch is executing. So in the else branch, it is returning all the values of base ID except this specific ID. On the other side, in the test case, when it is trying to run this assertion that is expecting to get all the base IDs, the assertion is failing. So to mitigate this problem, we propose a technique that can automatically update the assertions. In this paper, we propose UTFix that can repair unit tests when their corresponding focal methods undergo changes. Our UTFix addresses two critical issues. The first one is spurious assertion failure and then the reduced code coverage. For the evaluation purposes, we create two datasets. One is for synthetic dataset and another one is real world dataset. Now I'll talk about how our proposed solution work. So these four are our input to our UTFix. So here the first is original focal method, then updated focal method, original test code and the failure message that we find. And then we send this to the UTFix and UTFix can generate the updated test. Now I'll talk about UTFix in details. So here again we have the same input that I just said. And from the original focal method and the updated focal method, we measure the code diff. And using these informations, we create a prompt and that are fed to the LLM. And the prompt are looking like this. It contains a set of instructions, constraints and the data. And then LLM is generating a test code. Then we have a validator that checks if the generated test is correct or not. If it is a correct one, then we can directly take that test and we update the test code. Otherwise, we collect the more contextual information by the static and dynamic slicing. And then we generate the feedback considering all these contextual informations and pass it to the LLM. And we keep running this process until the chain of thought value is less than or equal 5. Now I'll talk about how validator works. So the input to the validator is the generated test, and then we have an execution validator that runs the test, and if the test passes, then we collect the code coverage. And then we check if all the change lines are covered or not. If yes, then we are very happy and we update our test code. Otherwise, if the test fails, then we collect the failure log. And if it happens that the test is passing but all the changed codes are not covered, then we are collecting only the uncovered lines. Now I'll talk about how the context gathering works. So here we have two process. One is static code slicing and another one is dynamic code slicing. The static analysis here we are depending on the focal file. So focal file is a file that contains the focal method. So using these three information, we create again a prompt And our prompt is looking like this. It contains the set of instructions and the data. And then we feed these things to the LLM and it generates the relevant code slices. Our relevant code slices are looking like this. And the idea of code slicing is mainly coming from the cohesion and coupling concept of the code design. And when we did that static code slicing, we still find that there are lots of relevant part of the code we are missing. So that's why we rely on the dynamic code slicing. Here, we run the test, we collect the code coverage, and then we find that the sometimes the coverage report is too big. That's why our minimization scheme minimizes the code coverage report for this specific focal method. Finally, it generates the code slices, and our dynamic code slices are looking like this. Now, I'll talk about the dataset that we consider that we created in our research. So, to evaluate the UTFix, we generate scene bench and real world dataset. So, we have three steps. The first one is we identify the focal method and the test code pair, and then the scene bench and the real world dataset. Now, I'll talk about how identification of focal method and unit test pair happens. So, here we collect the test code using the unit test loader, and then we collect the AST of the test code to look for what are the methods that are called from the test, and then we do the Jagged similarity index to look for what are the focal methods or what are the methods that are called from the test which are very similar. And that is one way, and also we rely on large language models. We pass the test body and asking the LLM that what could be the possible focal method, and then we do the intersection between this suggestion and our prior suggestions that we found by the Jagged similarity index. And then we collect the code coverage report, and finally we get 690 total FMUT pairs. And once we get that, now we will create our main dataset, that is scene bench. So, here the main objective is to change the inject changes in the focal method. So, here we collect the context is mainly the focal file, and here we are also emulating what could be the possible changes that developers usually make in their code base, and then using those informations we are guiding the LLM. And then here our intent is to measure that our UTFix is working when there is some assertion failure happens in our dataset. That's why we also instruct our intent to the LLM, and the generated code that we find by the LLM, we execute it and check if it satisfies our intent or not. If it does not, then we again give the feedback. Otherwise, we consider it is a valid instance of our dataset. Following this way, we get 352 total pairs. And for the other case, we also follow the same way. So, similarly, we provide the intent and we run the test. If it satisfies, then we are happy. We keep that instance as into our dataset. And in case of real world dataset preparation, here we mainly traverse the Git. So, here we see, for example, we have 9 commit history. So, we check, we start with the latest commit, that is C9. So, we goes backward. For example, first we go to the C8 commit, and then we find there is no change happens in the focal method and the test code. So, then we go back again, and we find that the code changes happens and it is a valid commit. By saying valid commit, we mean like no assertion failure in this commit. If it happens, then we replace this T9 to T7. So, this is how we create our real world dataset, and following this approach, we get 20 pairs for spurious assertion failures and 30 for the T-twist code coverage. And we have 5 total research questions, but for the sake of presentation, I will talk about only 2. So, for the details, please see our paper. And so, the first research question that I will discuss, that is how effective UTFix is in repairing failed tests and how much time it needs to repair the test. So to do the experiments, we have a baseline that has the updated focal method and the failure message and the original test. And for the UTFix, we make 4 different variants with the different contextual informations. So here our effectiveness, we see that when we have the UTFix with dynamic trace, at that time we can repair maximum number of tests, which is 314. And whereas the baseline is 295, and we also see that for other variants of UTFix can also performs better than the baseline. And for the runtime, we see that dynamic UTFix with dynamic trace, it takes a little bit more time than UTFix without any trace and with static trace. However, we see that it is better than the baseline. So we can say that UTFix with dynamic analysis is better than the baseline. And in conclusion, in this paper we present UTFix to repair unit tests that suffer from the assertion failure and reduced code coverage. We create 2 data sets, and we can repair 89.2% assertion failures, and we find the UTFix with dynamic analysis performs the best. Our code and the dataset are available in this repository. I'll be happy to take the questions for now and later. And I would like to also talk one more thing. So I'll be in the academic job market this year. I'll be happy to chat more about my research and for the future collaborations. Thank you.
Time for a question or two? Come up to the microphones.
So if there's a assertion failure, how do I know which I should fix, the test code or the program code?
Now so if the assertion is problematic, we repair the assertions only, the test code. We do not repair that. We are assuming that.
I mean, if I'm a developer, I want to use your tool, then in what scenario should I use? How do I know that it's the test code that need to be fixed, but not the other part of the program?
Yes. So here our assumption is the actual code is correct. The changes, whatever the changes is happening within the code base, it's correct. We are assuming that the test code is not correct or updated with the changes in the code.
Okay. Okay, thanks.
Okay, hi, Yunbo from the Chinese University of Hong Kong. So I love the idea of static code slicing, but I'm wondering if you have ever encountered any file or focal methods that's related to many other external functions. If so, would LLM understand such long context across like different files or even different projects?
Yeah. So you want to know sorry, would you please repeat the?
So I'm wondering if LLM can like process long context well, like in different files or in different projects.
So for the static slicing, so we are relying only the focal file. That means the file that contains the focal method. So we are not providing, that's why we are not providing too much context to the LLM. And we are limiting it to only the focal file. But later we realized that it is not enough because static slicing is missing lots of relevant code slices. That's why we rely on the dynamic slice. And here the problem, the thing that you are just asking, okay, what happens when we have loss of context? The problem, that's why we have a minimization scheme that minimizes the dynamic code traces so that we can give a reasonable amount of context to the LLM.
Okay, thank you.
Does this make, okay, thank you.
All right, let's thank the speaker again.
Thank you.